All right, so so we introduce this thing which is like, well, denoted by k hat. Basically, the idea is to take some x, tensor it with truncated polynomials, and then consider relative k-theory, and then go to the limit with respect to the power truncation. And this was introduced by Bloch a very long time ago, I think with two expectations. One, that this will be computable, and second, that this would be related to k-theory of x itself. Maybe not to k-theory, but maybe to, I mean, there is a conjecture that perfect completion of k-theory should be expressed in terms of this. So this was 4 years ago, and since then, so the first part was completely realized. This is indeed completely computable, and the picture is very clear. The second, I think, is still, it's not like there's no progress. I mean, there is a conjecture, of course. So let me ignore the conjecture, and let me just stick to the computations. And as I explained, especially since Thomas on theory, we know that this thing is actually very, very local. In fact, very stable. So to be able to compute it, it's sufficient to be able to compute it for ellipse. So I'm going to stick to this ellipse. All right. Now, so let me take a commutative ring. Just please let me right away assume that's actually an algebra of finite field. So P would be enough for me. So we have this completed K-theory. And let's see what happens. So in degree 0, for K0, this is actually 0, clearly, because is it clear? Yeah, I think it is, because you see those nilpotent extensions do not change at least K0, because every projective module is completely determined by its reduction model on the ideal, so it's the same thing, so there is the same set of isomorphs plus of projective models. So K0 is not interesting, but let's look at K1. So in the first part, my slogan was that you don't need to know the definition of K-theory at all. But here, we need to know something, and we need to know K1. And the basic fact is, so in general, K1 when commutes if A is some kind of commutative ring. Then the formal definition of K1 is the following. In fact, this is any ring, yeah. So for commutative ring, you can take just invertible elements, sharing 1. And this is already an abelian group. For a non-commutative ring, we can take GL1, this will be now a group but not a commutative one. We can take a stabilization. And instead of GL1, we can take JL. So we take JLM of A, take a stabilization, just take the quotient and take directly into respect to time. If A is commutative, then GL1 is just A star, right? So A star goes to Q1. But the map is actually split. There is a map in the other direction which sends a matrix to its determinant. Now, in general, it is not an isomorphism. In general, K1 of A is A star plus something else. But this something else, in the relative situation, also vanishes. Let me not prove it. And if you want a completely elementary proof, then I think you can find one in Miller's book on K-theory, which predates K-theory. So we have this. So for relative groups, this is another. When I say relative groups, I always understand that the ideal is important. So the relative situation, you have something important. Okay.
Then, what do you mean? I mean, what is units in the relative set?
This is the kernel. So there are units. What is so that is we have the following. So K1 of AI. We take A star. We take the map to A of I star, and we take the kernel. In this case,
Реализация или то, что просто элементарно.
ну, повторение реализации. Теперь мы right. So this K1 of A, the inverse limit. Well, I mean, this is take the inverse limit, but so A commutative. Then this is one. So you take form power series of one variable, invertible, respect to multiplication, and you consider the subgroup of those which have constitute term 1. Those are automatically invertible. So this is one form. And the group operation is multiplication. So this is known as the group of wheat, universal wheat vectors. What does it look like? So the basic fact is that if you consider FP, so this, first of all, it turns out that this is naturally a ring, so this is naturally a ring. And moreover, as a ring, if you compute it for FP, then the answer is huge, but it has simple structure. So it's a product of copies of just periodic numbers. And copies are numbered by all integers not divisible by 2. All positive integers not divisible by 2.
Нет, ты его уже определил, или ты его не планируешь, а ты считаешь, что все знают?
Ну, как группу определить.
Как группу, да.
Как так что некоторые определения на доске уже написано. Определение группы. Как вы сказали,
But for this general statement, you didn't care what the ground field was.
no. But this is true for FP, and there is similar decomposition for things over FP, but only things over FP. How do you see this?
Написано. В смысле, ты видишь, что это распределение одного и того же, как n.
So this is the product of the same, copies of the same thing, but just number, community number. So how do we see this? And now the statement that this has a natural ring structure, that's a more exact statement, is more meaningful. Let me be a bit more abstract than I strictly need now, because I will Эта штука является просто произведением копии n. Эта штука является просто произведением копии ZP. Одно и то же. Произведение по n. Произведение по n таким, что p не делит вот так. Так лучше?
ZP, но в большом количестве.
В большом количестве. Так, значит, so let me define one version of K-theory. It's general definition, so assume given some associative algebra R over some K and some R bimodule. This means module over R opposite times R over K. And this way I need to fix this K. And then I can consider the following categories. So take the category of AM modules an AM module is a pair pairs VA. So V is an A module. And A is a map from V to M. Sorry, A that was R here, R module. So what's the use of bimodules? Bimodules define those kinds of functors. A bimodule is a functor from modules to modules. So then it's fine. No conditions on the map, just any map.
I mean, not even a map of R modules.
A map of R modules. But no, it doesn't have to square to anything. Then I can consider subcategory which I denote as F of trying to generate projective. These are guys such that V is trying to generate projective over R. And this is a nice additive category. So I can take its K0. I don't need higher groups for now. Just take K0. And then an observation is that we can forget A. So every pair defines just an R module and projective. So this K0 of this category maps to K0 of R. And the map is split, because conversely, we can take any V and let A equal to 0. It's perfectly well. So what happens is that K0 of this category of modules splits as a sum of K0 R plus something else. And this something else let me denote by K0 of R. K0 of R of K0. So this is the definition.
And if M is a two-sided ideal,
Then M is a two-sided ideal.
doesn't it?
Yes.
Then does it have? And now we have two.
Doesn't agree with.
Yeah.
Ah,
Then the symbol means two things.
Yes.
A priori.
no. It's a bad notation. So the relative thing should be
Put a semicolon.
This is kind of standard. So this was this. I think the first person produced by Dundas and McCarthy, something like 92 or so. Dundas and McCarthy, some topologists. Well, topological topologists. And to make things worse, this is related to some kind of relative K-theory of 3 square zero extension of R by A. So anyway, but so this is finished. And then when you have guys like that, you can take another product over K. So if you have R1, M1, R2, M2, then you have a product. In particular, to just take K0 of C. K of coefficients in K, that is zero. It's an associative ring. In fact, it's also a unital ring with unity given by K, and then this A. So it should be a map from V to M tangent V, but since M is the diagonal bimodule, this is just an endomorphism of V, right? So I take the identity. And in general, this thing is the following. We take K modules plus an endomorph. And we take a K. You might think that this is the same thing as endomorphisms of, I don't know, polynomials and non-generative. But this is not true, because what's crucial is the finiteness condition. So here we say that the thing is finitely generated projective over K. So K0
Here is this K or R? And then that's over R.
over R.
Okay. And here R equals K. And this is
Here R equals K, yes. So this is not equal to this at all. Although by definition this is something, a K-theory of something, which is a module over polynomials. This module is certainly not projective over the polynomials. In fact, it's like finite dimensional. If K is just a vector space, and this is finite dimensional over the polynomials. So this is completely different.
so supported on some points on the line.
Supports on some points on the line.
Strictly speaking, this is K identity minus K0.
Sure. But still very, very different.
Right.
So supported to some points on K star effect, because we took out the part which is supported. Right. And in fact, this is easy to compute from this observation. So to support it, this is like find a subset in K star. And since we take K groups, it doesn't matter. So we will allow extensions. We will not allow for extensions. So the only thing which matters is multiplicity. So
Set of points in multiplicity of each point.
Yeah. So basically, this is just a free abelian group generated by vertical elements. And if K is of the very closure over P, then this is just free abelian group generated by roots of unity to the degree, right? But what I want to make a different observation. I want to say that every endomorphism is basically a matrix, and every matrix has a characteristic element. So we have a natural map. Natural map. And K0, now let us specify what we want with it. Well, no, for now it is to K. So we have a map of this to double vector. So VA. So let's say that K is a field. This is just K to the power n. So this is a matrix. And I want to take the characteristic polynomial of this matrix, except that I want to have constant term 1. So what I do, I change variables. So I take determinant of identity minus T.
So VA minus V0. Because otherwise this is not an element of VA is not an element of K0 RF because
I define a map on the whole thing and then restrict it.
okay.
Because if you take A equal to 0,
This is
then this is identity which is 0 now.
Yes.
So this is consistent. Alright, now in fact, we can do slightly better. So this is a ring, as I said, and this ring actually acts here. Just because if you have, I mean, the category of some guys acts on models over truncated polynomials. You take tensor product and twist T by multiplying it with K. Now I can state a theorem. The product in the scale 0 of K. Okay. Let me stick to extends uniquely to continuous product in W of K. Continuous in the following sense. So this thing appeared as some kind of reverse limit, right? By power.
Actually, also this map is injective and its image consists of polynomials.
So this is reverse limit. Wn of Q, where this is just the same thing located at that, right? So it's 1 plus T. So, all right, so what's obvious, at least for the case of the field, is that this map is indeed injective, and the whole thing is the completion of this thing with respect to this topology, because this consists of all power series. These, of course, are only polynomials. But the observation is that if you take any power series and take it any truncation, then you can approximate it by a characteristic polynomial of a big enough matrix. So once you prescribe first, I know, n coefficients of a characteristic polynomial, you can always find a large matrix with this characteristic polynomial, plus maybe something else which you don't have. So, and adjectivity is also, I mean, you have to check it, but
It's not so trivial. It's
technical, yeah. It's a bit technical, but it's true. So uniqueness is sort of obvious once you have this. Existence you have to work for. That's also true. I won't do it. But I will use this to compute that decomposition. Because you see, it's kind of clear from the definition. So every formal power series of constant term 1. So every T in A plus T K of T can be written Actually, let me state that this is actually true for anything, for any equation. And let me take z instead of fp for now. Make the statement static to million. Then every form of our series can be written uniquely as the product of the following form. So you take 1 minus e to the power n to the power bn, where bn is certain. So this you prove by induction on n. This means that as a group, this W of Z is a product of copies of Z numbered by integers. Those coefficients here. With the generators given by objects. So let me write this instead of this. Let me write this in the following way. Just all infinite, possibly infinite linear combinations of generators, and the generators are the classes of those things. And then the observation is that those guys actually come from here, and it's easy to compute their products. So this completely determines the ring structure. Namely, that is a characteristic polynomial of the matrix of the following form. So we have identity. So size is n, and now I have the, so for n-dimensional vector space, I have the transposition. Those are below the diagonal. No, those are on the diagonal, but those are not all. So I have the transposition of order n acting on t just by producing the vectors. And this will be my a. So I take minus t times this transposition. So it's minus t here, minus t here, minus t, and then there's t, there's minus t in the bottom left corner. And the rest is 0. So this is the same as identity minus t sigma, where sigma is the permutation. So this is this. And this defines a class of K 0 of Z. And to compute the product of two generators, I just need to take two matrices like this and compute the other product. And the answer is clear. So what happens is basically you have a set with n elements on which you have this permutation action. You have another set of m elements on which you have this permutation thing. And then I take the product of those. I let sigma be the product of the two sigmas, and I check how the product decomposes into orbits with respect to the range. And of course, if say n and m are co-prime, then the action on the product will be transitive. Conversely, if I take if n is equal to m, if the two sigmas are the same, then the product will decompose into n copies of the same orbit. And the general answer is that this times this will be, so let me denote by m, there is a multiple of m, then this will be epsilon m, and the not least will be the greatest common divisor. In particular, epsilon n square is equal to n epsilon n.
Up there.
Ah?
Is it n times n or n times n? In the first place.
So this was for any particular function. In fact, completely changed. But now, and the construction is functorial, so I forgot to say this part is functorial. So when we go from W of z to W of say f, we still have the images of those epsilons, which generate the form. But now, as a group, this thing is clearly P-local. Just by definition. In fact, you can check that Wn is an extension of Wn minus 1, and the kernel is just K. K in this case is inherited by P, so by reduction, all the Wn's are P-local, so you have this P-local. Which means that if n is not divisible by P, you can produce an idempotent problem. This is an idempotent. So it squares to itself. And homomorphism. Oh, this double. And this is what gives the composition of the product of copies of the same way. So what happens in fact is that plain the more properties. So the property is that now as a ring, this is the product of copies of the images of those idempotents. So copies of ZP, and this corresponds to the system of commuting idempotents. Over n epsilon n. It's not true that this is the image of this, because those idempotents are commuting but not orthogonal. So as usual, we have to take some kind of combinations to produce an orthogonal idempotents and then decompose the problem. And more generally, for every algebra A over P, we still have those epsilons, and the ring is still P-local, so we still have those idempotents. And in fact, a more difficult proposition for any A over P so very important. One over n epsilon n give a decomposition W of A is equal to the product of copies numbered by those integers not divisible by P of the same ring, which is denoted by usual W of A, and can be described, well, I don't know, for example, as a common kernel of the idempotence. So the point is that idempotents, of course, induce a decomposition like this. And the claim is that all the terms of the decomposition are the same. And the simplest one to write down is the just common kernel of all those things. So it's the intersection over n of the kernel of 1 over n epsilon n sitting inside z over the positive. And this is called the ring of p-typical with and then the claim is that if A is just Fp, then this p-typical ring is just J flowers. Now this is what we discovered with a completely different definition, different properties. And in fact, this can be defined for any A, not necessarily over P, but then you won't get a decomposition. You will only get some A. And then later people realized that you can put the constructions for various primes together into a single construction like this, and we recovered the original one by this. So this is the explanation for the p-typical board, which I can entitle talk. Okay. Now I have to combine. So I have curves most break theory, I have the notion of the p-typical, so I have to combine the two. And I can now take a definition. So as I said, those idempotents act on this completed K-theory for any commutative ring. In fact, for any ring at all, because you can take it if you have some vector space of endomorphism, and you can have some modulo or some ring plus one form of variable T. You can twist, you can tensor the modulo of the vector space, twist T by the endomorphism A, and this gives you an action of this K0 of KK on the K-square. In particular, this applies to this K hat of X, which I had before. Now I need a different notion. So I use this for localization already. So the square brackets of X. And this is by definition the kernel of the intersection over all that is not divisible by P. And the kernel of those idempotents sitting inside K hat of X. So these are p-typical curves. In algebraic K-theory. Okay.
No, so we said that there is an action of K with two arguments, which
yes.
are bimodal. We know that this ring is dense with vector.
Yes.
We continue the action.
For this, we don't even need to continue the action, because all those idempotents already sit.
Okay, that was it.
But in fact, you can continue the action.
What's the argument again for A?
It's not again because I didn't say it. I just I said it, but didn't write it. Let me explain. So we want to act on this thing. So we need to be able to act on truncated. So we have some A, say star Dij algebra over T, mod Tf. Right. And we have some M here. On the other hand, we have some VA, where V is a K vector space finite dimension. And A is an endomorphism of V. So we can consider M times V is a module over, again, A T net C N with the steep twiddle acting by well, A times T T times A, maybe, yes. But this is clearly functional on both arguments. And using this general notice about K-theory, we see that K, at least, I mean, higher K-theory also, but at least K0 on this just acts on K-theory on this, on all K-terms. And this gives me my
Say why curves?
Curves. Because of this parameter, we kind of test on great variety by looking at, the Bezier curve. I mean, it's not a good reason, but
It's kind of in that direction. I mean, it's away from spec right.
as block, it's his terminology. Right. So this is the definition of it. And so these are important. So this is just a direct sum here canonically. So all this thing about localization, blah blah blah, it all just immediately generalized. Now, the interesting question is, I started with general algebraic K theory, and then I only considered K1. And why do I do this? Well, the stupid answer is that K1 is simpler. But the much more interesting answer is that it's all there is. So we already know that this vanishes for in degree 0, almost always. In degree 1, this is a large thing which is interesting and so on. And then the higher degrees is also equal to 0. And there is no direct proof to this. At least I don't know one. And the only proof I know is to prove some generalization of this. Even for that, the argument is very indirect. And so I think at least there is a published proof of this and of the generalization also by Kesselholt. It's also extremely indirect. It is also. That's a positive approach. Maybe for this fact, not for generalization, you can find some proof in the literature, but I don't know. It's basically it's a fact about homology, right? We need to consider JLN over FP over one variable. So we take the determinant. And the claim is that the kernel has no homology. I don't see any reason for this. It would be very nice to do it. But, so I won't give you a proof even of generalization, but let me explain what's a generalization. Because it turns out that in order to compute this thing, the current generalization becomes very difficult. So if you play the game correctly, you can trade basically allowing coefficients for no need to compute current coefficient. And then there, the whole game reduces to K1 of something, which is within human power to compute. Okay. So generalization. Assume we're in the following situation. We have some K algebra. K say Q. And we have some R by module, which we assume to be projective. projective, my model for me means projective as a model over the whole thing. It's a model over R over and it is projective. So right away, even if K is commutative, the diagonal bimodal is never projective unless R is a finite extension. And in general, this is the structure shift of diagonal. So what I'm going to say in the next few minutes does not apply directly to the case of interest products, to the case of bimodal. But nevertheless. Then we consider. So the idea is that to generalize the weak vector construction, we need to generalize to allow the ring to be non-commutative, but also to consider polynomials in several variables. And the important thing is to allow those to take those variables non-commutative. So what we do, we consider the terms of algebra of the bimodal M of the algebra. So by definition is direct sum. You know, if I have a bimodal, it contains tensor product with itself over R. This gives you a gradient algebra. Okay. Now, of course, here we have the ideals, precise ideals spanned by all guys of degree and because it's a gradient algebra. So definition. So I need some kind of name for this. Probably with K-theory serve. Let me not give it a name, but let's give it notation. Notation would be WK of R and this will be the inverse limit over N over truncated version of itself and the truncated version will be the following thing. So I take tensor algebra modulo of this ideal. Here I have the ideal generated by t greater or equal to 1. And I take relative K-theory.
Which ideal again the last? Which ideal the last
one?
Of t
Ergo of positive degree. T greater or equal to 1. Model again the same thing. So I take out everything of degree n and bigger. So I obtain some gradient which is actually an important extension of R. So I have degree 0, R degree 0, then degree 1, 2, blah, 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 up to n, and then I take the rest of it. So this is an extension of R by an important ideal. So I take this important ideal, and I take the relative K-theory. In fact, in this case, this extension is split. So there is a map from this algebra to R. There is a map back. So K-theory of the whole thing splits as the sum of K-theory of R plus the rest. So I want the rest. That's my W. In fact, in this definition, I don't need M to be projective over the whole thing. It's sufficient to have it. So I need to take those tensor powers here. So it's better to consider bimodals which are, for example, projective over the left action of, or the left action of R, or the right action of R. So that this tensor product is not the exact one. So in this definition, I can't even allow the diagonal. But then the theorem is that the theorem generalizes this. is that this thing vanishes if M is projective. So they are opposite. So the whole thing reduces again to K1. So what? So the interesting thing here is what happens in K1. And let me denote this that by W of, so I need two variables M and R, so it's W of M over R. Plus W of 1. And let me state right away that again I have this so this twisting of the randomism which I have for modulus over power series in T. I can also do it here. I can twist the action of the tensor algebra with the same intervals. So the same procedure gives me an action of K0 Kk over this value. So here I can also have those idempotents. I can also take this p-typical differentiation. So we also have W of R and the term inside the whole thing and which is again the intersection of the kernels of those elements. So what can you prove about this guy? So there are three things which give the series to compute very effectively. So fact of level 1 when one appears a product on those guys, which is naturally respectable variables, but let me state it slightly stronger. So observe that we have a natural map with term character map that we want from K0 R K-theory of coefficients to W of M over R. Maybe if we have EA, then you can consider the model over the present algebra. And so this is K1, so I need an element of K1 of the tensor algebra. So this is a projective model of the algebra. And then this A defines an endomorphism of T, denoted by AT of that. Well, it's a projective basically freely generated by V, so to define a map, a map which is linear over the tensor algebra from this guy to itself, it's sufficient to give a map from V to the whole thing. And this A is a map from V to M tensor V, which sees here as component of degree 1. So this T1 is the finish. So every A extends to an endomorphism of this guy. And then I want to take take, well, what we call the determinant of identity minus a tilde. But this determinant is actually fake. Because if you remember, the definition of K1 of something is the limit of mobilization of GL. So if I have some ring and some matrix of this ring of some size, it gives me an element in one of those groups. So it projects stabilization and gives me a natural element in K1. So in the commutative case, this is the honest determinant, because the honest determinant gives a map from this back to a star. But in the general case, every matrix at least gives me, invertible matrix, gives me a well-defined element in K1. So this is what we take, call it term of zero. And then we have two guys, and I take the direct sum. Then the general determinant is also clearly additive. So if I have direct sum of two things, then the corresponding matrix would be the direct sum of two matrices. And this would give me the product in K1. So this gives a well-defined map from map. So this has product, just because you can take tensor points of those together. My claim is that there exists a unique factorial product of the following type. Extending the product. So such that the chart character map is multiples. This is fact number one. The situation here is kind of strange, so I can prove it, I mean, as stated, that is W, which is comes from K1. But the construction is not factorial enough, and it's not clear to me whether it extends to higher K-theory when M is not projected. Well, a posteriori it does, but I don't know any reasonable construction. Что?
Конструкция превратилась из чего, получается?
Ну, ситуация такая. Во-первых, образ Черна, ну, по крайней мере, в простых случаях, таки плоть. So the image of the Chern character map is actually dense. So it's injective and the image is dense. But I absolutely have no idea how to use, how to prove that the product extends. So this is completion with respect to certain topology, which is a very strange topology. I don't have a good description. In particular, it's not clear that the product extends, so there is a completely different construction of the product. And this completely different construction is also completely different already in the usual case of vectors. And this uses some kind of, I don't know, state residue.
Actually, you defined all the stuff. You have defined all the stuff before without being key theory. So you use the same construction application.
Yeah. I mean, for usual vectors, you don't need to know that there is any key theory. Although the construction of the product, I think uses key theory. Yeah, it does. Some kind of key theory. But this very strange construction only works for tensor algebra, not for the completed K-theory, just to work the K-theory of tensor algebra. And then we have to work separately to show that it extends to completion, but that you can do for K1. And it's not possible, that's impossible to do it right. It's really very strange situation. So it's not clear to me what's going on. So this is lemma 1. Now lemma 2 is actually easy to prove, but this is very important because it's really helpful. So assume we're in the following situation. We have R1, R2, and we have some M1, 2, on which this guy acts on the left and this on the right. R1 times R2. And we have M21, where they act in the opposite. And assume that both are projected. Then you can do two things. You can take the tensor product over R2 and this will be something on which R1 acts on the left and on the right. It's a boundary. So I can consider this now. Or I can do it in the other direction. And do this. And the claim is that both are canonically the same. So then, now this is actually not possible to prove on the blackboard, but still I will not do it because it's late itself. But this is not the one that. But this helps enormously because you see, in my definition of this guy, I restrict my attention to projective modules, and projective modules are all direct summas of free modules. So if I take some projective R module, generated by some just K module V, then this thing allows me to express W of M over R in terms of W of something over K, namely W of R times V over K. Why is this? Well, you just take R1 equal to R, R2 equal to K, and then you arrange this and this, so according to one direction is this, and then according to the other direction is just this. So if we have some information about this functor for arbitrary, say, vector space over a field K, then a posteriori we obtain information about this thing over any K algebra. And then lemma 3, which is easier. Again, will gives you this information about this guy. So we have K, which is of Q, and some vector space. And by the way, it doesn't have to be a fine dimensional vector space. Vector space of any size. Then, well, it's not like you can completely write down this W, but it has a natural filtration because it comes as an inverse limit. And you can characterize the associated weight coefficient filtration. So for any n, we have a short exact sequence. That means we have Wn, so P over T goes to W n minus 1 and V over K. The net is subjective, and the kernel is the nth cyclic power take the
Co-invariants or
co-invariants. We take the m tensor power, and we take not the symmetric power, but just the cyclic power, the quotient by the longest permutation. So this has an associated, this has a filtration, the associated great quotient, this kind of the cyclic power of vector space. So this answer is maybe familiar to people who saw some computational function homology with tensor algebra. And the answer there is exactly the same. So function homology with tensor algebra generated by symmetric space is exactly the sum of those cyclic powers. Function homology in degree 0. And this function homology in degree 0 is also the same as cyclic homology in degree 0. Also known as additive K-theory in degree 1. And then the claim is that the genuine K-theory has a filtration because the associated quotient is the same as additive K. And this additive K-theory, by definition, is obtained. You take the same definition, but you replace the groups GLM with the Lie algebra GLM. And you take, instead of taking group homology or optimization, you take algebra homology. So the statement is not completely unexpected, but you still have to work a little bit to prove it, but it's not so difficult. So this shows you the setup. All right. And now I think we can collect all this stuff together. Collect all the stuff together to obtain finally a computational moment. Then the computation of this complete K-theory for computer. So recall that I had this weak K-theory. R M. This made sense for any bimodule M, at least different for any bimodule which is like, say, projected respect to the left x. And then the claim was that if M is actually very nice, and namely projective over R opposite times R, then this thing is only non-trivial in degree 1. But this is enough to recover it for any M by the following trick. So replace M in our bimodule with a projective resolution. And the claim is that this can be generalized to complexes, and then it's independent, it's the same for quasi-dimensional complexes. So in order to compute this for any M, you just need to replace M with a projective resolution, and then compute it for projective bimodals, which we know how to do. This will reduce the Q1.
for perfect modules, and there should be a finite resolution.
Right. So it's not trivial because this function is not additive in that. Right? Just absolutely not additive. As you see, it has a sort of cyclic power in its rates. So it cannot be additive. So when you cannot just apply it to a complex term. But it's well known how to do this. There's this trick of Dole. It's a Dole-Krohn equivalence between. Well, it's actually for any for the closed additive category, but let me do it for bimodules. So on one hand, you have complexes of R bimodules. Of arbitrary length, but concentrated in non-negative non-negative homological degrees. So it's 0 and 0. And on the other hand, there is simplicial R bimodules. And it turns out the two categories are equivalent. So for any simplicial bimodule, you can take its what's called normalized chain complex. So you write down the usual formula where the differentials there are the sum of the base maps, and you take out all the units of the degeneracy. And the claim is that this is an equivalence of categories, and the inverse equivalence of the claims that this is a generalization factor. And what is good about this category? So here, what's a complex? It's something with differential which squares to 0. When you apply some complete non-additive factor to this condition is additive. So it's not clear why it's preserved. Even if it's preserved, it's not clear why this is not to do. Because, for example, the notion of chain homotopy between two maps between complexes really uses some kind of it's a formula which has some sums of it, right? So when you apply some kind of non-additive factor, it's always correct. Whereas here on the simplicial side, it's just a function from some category to R by modules. And here, additivity is not used at all. It makes sense to consider simplicial whatever. Sets, topological space, same. And for any function, you can just apply it to something simplicial, just pointwise. Just apply it and we get it. And then the theorem of Dulp is that if you have two complexes here, which are chain homotopy equivalent, and you have a function from R by modules to any category, so any function from R by modules to any category G, you can generalize it to complexes of bimodules sitting in 180 degrees. By going here, applying f pointwise, and going back. So I have some function like this, and then this f applied, I write it like this, applied pointwise to simplicial objects. So take d, apply f, and then. So this is a function from complexes of bimodules to, well, it's better now to assume that this category is additive, so this makes sense. And then we go to complexes in E. So both categories are additive, but the factor can be arbitrary, as complicated as you want. But the claim is that this is nevertheless well defined in the sense that it does not depend. So it's this reverse chain homotopy equivalence. So it sends homotopic maps to homotopic maps.
What's that for?
Yeah, any additive category whatsoever. So this gives a procedure for generalizing, considering derived functors of non-additive functors, and this is what Dulp wants. We have some functor. We do the following: we take an R by module. We take its projective resolution. We apply this thing, and the result does not depend on the choice of projective resolution because any two are chain homotopy equivalent. And this is what works here. There's a morphic to the derived function of just the usual, of just K1, of this. So this is both derived. Should I write it on blackboard or is it clear? So we do this procedure with the choice of projective resolution. We extend this W as a function of all bimodules now, and then the claim is that we get this. And
Here R. It's just an associative algebra, it's a commutative algebra, associative. Now what if it's a VG algebra? And I want to define this thing on perfect complexes M over VG algebra R.
then you're in trouble because I mean, you can do it, certainly. But the claim is about
not via this procedure. Not using this procedure, or
no, you can never define using this procedure. You can't compute it.
because you only
So
no, but I mean it's always somehow you have this boundedness.
No.
So, I mean, if R
You
is an
cannot
algebra,
reduce it to K1. So that claim about the thing being reduced to K1 in some situation will not be true anymore.
but I just don't understand what it means. So suppose if R is just an algebra thought of as a stupid kind of DG algebra, then you're looking at DG modules with some kind of boundedness condition, so bounded above at 0.
So there are two things you can do. There are two things you can do. Right. So let's extend this to let's keep R. Let's keep R as a ring, but let's allow M to be complex. Then there are two things you can do. One, you can apply this procedure, right? So you can consider M and W of R. So basically you have a complex constrained in non-positive degrees, because otherwise it doesn't work. I mean, non-negative, non-logical. You go to simplicial, you do this double, you do it's one procedure. You can do completely different. You can take the definition and consider the standard algebra. This is a DG algebra, right? But so what? We know how to define the K-theory for DG algebras. So we can consider K-theory of this, we take the limit, this we have to truncate, and so on. We can do this. The problem is that there is no way to check that two are the same, and in fact, I'm not sure they are, even for a ring. In fact, K-theory of DG algebra is extremely painful to compute. The main reason for this is that for rings, there's this theorem which says that computation reduces to projective R models, or even if you forget about K0, to free R models. Essentially, it's about matrices. If you look at the definition of K-theory and DG category, you have to consider perfect modules. You have to consider all of them, which means you have to consider things which are extensions of free pairs, and no longer free themselves. And then you basically lost. At least I lost. I don't know what. So, for the record, at the moment, I have no idea how to compute this in the most trivial cases. Like, for example, we just take a bimodal shifted by 1. For that matter, I don't know how to compute K-theory of the DG algebra, meaning K of T, mod Tn, T single generator of degree, I don't know, 1 or 2, whatever you want. If somebody tells me what's this K-theory, I will be very good. That's simple. I think it's not to me, it's not clear. This you can compute, because this reduces to the question of numbers. And when you generalize your R to be DG algebra, there are all sorts of games you can play. They probably all give you different answers. And if we knew that the answers would be the same, we would prove all the conjectures already, and it would be true. Okay, so this is very nice. This is easy. But there is one, so this statement, there is one non-trivial fact here, which does not follow from general orthodoxies. So the non-trivial fact here is the following. If I do this, and here, and this is a fact. Let me even write it here. So I take some M, which is a complex of bimodals in a negative degree, and I compute the normalization of W applying pointwise the normalization of X. As we know by general theorem of Dole, this is changed homotopic invariant. So we have two complexes which are changed homotopic, and this is almost tautology. But the stronger fact is that we should have to prove is that this is quasi-isomorphism invariant. Some invariant under quasi-isomorphism. So, except that here it has to be with this two theorems. R of K-teachings. So I take this K-theory which I want to compute, I generalize it to complexes by this procedure, and then I prove that this is invariant on the quasi-isomorphisms. After that, I can replace anything with projective resolution. And what I gain is the fact that now I can reduce to K1. And this is why these higher K groups for an arbitrary model can be computed by using just K1 for terms in projective resolution. And that's how it is.
Isn't this Dole thing naughty?
Ah?
Isn't this Dole thing naughty precisely in positive characteristic? So what if you took symmetric powers for F?
Dole thing, the beauty of the Dole, this is true for any canonic closed additive category and any additive corresponding.
Right, but it doesn't compute the thing you expect it to, say for symmetric powers.
I don't expect it to compute anything. It's a definition.
Well, take F to be symmetric powers.
Yeah. This gives you a function.
And do this on complexes and positive characteristic.
Yeah.
Well, you have homology at the symmetric group and positive characteristic, and so you should expect to see that when taking symmetric powers in a homotopy way. And if you do this Dole thing, then it's not there, right?
The answer is the portion with respect to symmetric group or a certain thing quasi-isomorphic to the usual candidate. But not isomorphic. Yeah? No, it's a very non-trivial generalization. It's a pain to try to extend to all complexes, for example. Sometimes you can do it, not always. It is something which is very, very hard to control. But it works in this generality, so at least gives you something which is very different. And so, to cut the rest of the story short, actually I'm almost finished the story anyway. So let me just give you the answer for it. Okay, so definition. How should we read homology? Laying out coefficients by module M is the Dole derived functor. This is vectors. And the same for the typical parts, and also there's truncation, so there's WN here. So it works. Theorem, which I kind of explained here because it's always one of the things that.
How does it depend on M?
On M?
Yeah, there's no M.
So here. Theorem is that this computes. So here theory. We'll shift. Because the story starts with K1 and K0.
What's the difference between that corner and your definition?
This and this.
Yeah.
Here, by definition, I have to take projective resolution. So the trivial fact is that, so here by definition I have to take projective resolution, and then only take K1. Here I take, I don't necessarily take, here I take just the bimodule, but take all the K groups, including the higher ones. Then there are two observations. Two things to prove. One is that if I allow a complex here, then the result does not depend on the complex after it carries over. Not only homotopy connect, but quasi-isomorphism. So I can replace this guy with projective resolution right away. And observation second is that if this thing is projective, then I don't need higher K groups. I can just take K1. Because of this is looking for this. By definition, this by definition is just WK1, right? And when I take a goal direct, this means that I only use projective complexes.
Yeah, but I mean, what is the difference between so this big portion group is it the same as
this is just this here.
yes,
So I take M, replace it with projective resolution, and then the precision.
it's an extra notation.
Ah,
It's only an extra notation.
true. So the reason for this notation is that the following proposition. Why Cauchy homology? So this, as I said, this also has truncated versions, right? Because it's in Miller statement. So W1, which H of R and M, is exactly the usual Cauchy homology of R and M. So this whole thing becomes extremely computable. Especially, so as I said, you have to replace something with the projective resolution. If you take the bar resolution, for example, you can control the size of essentially graded pieces of these groups rather easily. It will be computed by a certain explicit complex similar to the usual Cauchy complex. In particular, in degree 1, this will be just the Cauchy complex of the letters. And the general comparison theorem is the following. Now assume that we have some A which is commutative. Finally generated this finite K, characteristic P, and smooth in the sense that correspondence algebraic variety is smooth. Then we have canonical identifications between. So the theorem is for p-typical version of this guy. Of A with coefficients of A in degree prime. We have a matrix theorem of the type of F0 X as the type of X. Now, as I stated here, it's a theorem, and I have to explain what this guy is, although it's logically it should be the definition. And then the theorem would be the computation of this theorem, this and this and this. But the point is that this is something which was invented by Luzier for involved. It's something called the round width complex. So a certain refinement of the RAM complex in characteristic 0. Sorry, in degree 1. So W1 is just the RAM complex. So just one X. And then UZ has constructed a certain projective system of refinement of the game, of extension. It has all the structures that the usual RAM complex has. So it has multiplication, it has a differential. And then my theorem of UZ is that if you consider complete homology of your variety of partitions in this complex, in this differential, this will be crystalline homology of X. That's defined correctly. So this was a way to compute crystalline homology.
This is X smooth. X smooth.
Yes. And crystalline without rigid order. Just crystalline with rigid order. But I mean, this is true for not fine, there is no homology. This is true for everything.
And here in this theorem, this is just H0.
Yeah, because this is a file. This is just short.
Do you have a theorem like this?
Well, I don't have a left side. In non-fine situation, I don't have
What's
what
the
is
problem in defining this?
all sorts of problems, like it starts with the algebra and the problem. And as we discussed,
So you have something on the product of X cross X. Is there some fundamental reason this is not lovable? I mean, all this Boltzmann nonsense is true in the category of coherence.
it relies heavily on the fact that something is true for projective. I mean, you don't have projective generators in the case of the to begin with.
Sure.
No, you can do a version of this for DJ objects, but this is kind of non-trivial.
And can't you just... So how do you do it for Hochschild homology in this scheme? You define some sort of local version of Hochschild chains.
Hochschild homology basically takes this as definition. Define local version. So if you want, the statement is that this is the local. So this is local state. This is a statement that local. If you compute locally this, so this effect about p-typical part of K hat, right? Basically, this is the statement that if you compute it locally, then you get this. That's it. I mean, again, what else? You can do two things. You can either do it locally on your variety. Okay, fine. As we see this we have localized this file. Then you get this thing. So this is, I mean, maybe the confusing thing is that this is stated for a given x. But in fact, it's a local statement. Or you can try to generalize it to TG. Using the usual month, the version is derived of that. I find it derived sense. But then you run into the problem of how to define this kind. Because, as I said, the construction is heavily used this non-empty function, so it's kind of. Roughly speaking, I do have a procedure for extending homology theories like this from algebras to DJ algebra, which works and gives something which has localization of that sequence. But then it's not clear how this relates to K-theory. And then, or you can define this K hat, but then it's hard to compute it for a train of DJ algebra. So if you have a great variety, which has some kind of heuristic topology, then you can localize respect to heuristic topology. You just have some kind of active DJ algebra, then you can still define K hat, but there is nowhere to localize this. So there is no way to reduce it to something for radius. So this is the best way. And then to see, in fact, in order to prove this, so you need to see those extra structures. So this guy has, as I said, has derivative differential roots here. And also it has some additional structures, so some maps denoted F and V, which comes part of the package and then needed for the finish way. So all this exists in this generative fragmentary theorem. And in particular, the differential comes in the same way it comes in the cyclic homologies. So you have Hofstad homology. So for Hofstad homology, this is just for W1, this is just Hofstad theorem. But then we know that Hofstad homology has more structure, it's actually a cyclic object, which generates the consequent differential. Exactly the same happens here. So this, for an n, this thing is actually comes from such a cyclic object, which has this additional differential.
Is there also a WHC and a WHP?
Sure. For sure, and also you have those additional structures that have done so these also that you have them here that have a very transparent interpretation. And so to me it looks like this should be the definition of dynamic calculus. And then crystalline homology is just something that really that complete WHP or whatever that logic is. Right. Okay, that's it. I think that's it.
Ну, мне кажется, можно еще там
Thank you.